So today is February 9th? Yeah, February 9th, 2012, and this is AP Statistics at CASA. We're going to start Chapter 10. Chapter 10, the idea of comparing two populations or groups using inferential statistics. This chapter only has two sections, so we're going to get through this relatively quickly. Like by the end of next week, we're going to get done with this chapter. And on top of that, that means that I believe you only have two more chapters to get through after midwinter break to be prepared for the AP exam. By the way, we'll be collecting money for AP exams relatively soon. So today we're only going to be looking at comparing two proportions. When we do the 10-2 lecture, we'll be comparing two means. All right. In this lecture, what we would like to start off with is the foundation on which we're going to build the inferential statistical techniques called a test for the difference of proportions, or a test for a difference, or a confidence interval for a difference of proportions. So first we're going to build some foundation, and then on that foundation we're going to build the confidence interval and the significance testing techniques. But let's start with our basics. In this chapter, not only for this section but for the next section, we're going to be talking about looking at two distinct populations and then trying to do a comparison between those two distinct populations, or two distinct groups. And I use the word groups instead of populations in the sense that we're going to be using these techniques also to verify the ability to test things experimentally. Do we think between group 1 and group 2 that providing a breakfast before school helps people's grades? So we have groups that people who are getting lunch or breakfast before school, people who are not getting breakfast. But we can do that in experimental sense. But the idea is that we have two groups, and we want to say, are they different? Is there something going on there that's significant, that is not explained by pure chance alone? So, population 1 and population 2. Now, within population 1, we're going to have something called P sub 1. Now, what do I mean by P sub 1? Well, earlier in the year, we used P to say a proportion of something, proportion of population. The proportion of the population that is left-handed, the proportion of the population that is plays an instrument, the proportion of the population that arrives tardy to school. Say, some subgroup of a population. Now that we have two distinct populations, now we can say, what about the proportion of that population just within, or what's the proportion within that first population? Does it make a difference between being a male or a female whether you arrive late to school? So on any given day, some proportion of the students arrive late. Amongst the population which are female, I want to talk about their lateness. Oh, P1, the proportion of the females who were late. Amongst population 2, I've got P sub 2, the proportion of the males who were late to school. Okay? So we're studying some aspect, categorical in nature, about distinct populations. Also, we could describe the group as the two groups that we're studying as a treatment 1 group, treatment 2 group. Does acetaminophen help reduce headaches better than aspirin? So we give one group one treatment, let's call that population 1. We give the other group the other treatment, let's call that population 2. And then we say, okay, what proportion of you still have headaches? P1 is the proportion of people who got aspirin who still have headaches. P2 is the people in the acetaminophen group that still have headaches. But two distinct groups and then proportions within those groups. Let's summarize the symbols that we're going to be using in this. Within population 1, we're going to use P1 to describe the proportion, population proportion. What if we could have tested everyone? Now, We don't test everyone because
Can't do it. No,
Two-
not
not enough time and not enough
money.
money. Right? So when we test only a subgroup of that population, when we test only a sample, we get a proportion, but it's a sample proportion. We had used the letter p hat for that, but now since we have two distinct populations, we'll call it p hat sub 1. The sample size that we take out of that population, we'll call it n sub 1. Similarly with population number 2, p sub 2, the proportion as if we interviewed everyone in the population. P hat sub 2, what was the sample proportion, and then n sub 2, what was the size of the sample that we took out of population 2. Okay, so we're going to be throwing a lot of symbols around in this section. Tell me when you are ready for me to continue. Does anyone need any more time on this slide? We good? All right. Let's continue on then. Okay. Let's talk about the distribution that we're going to be using to do our probability calculations and our confidence interval calculations. It's called the distribution of the difference of proportions, or distribution of the difference of sample proportions. Now, we're going to build this idea slowly, and let's start with the things that we know. Not this big one, ready? Not the distribution of the difference of the sample proportions, but let's talk about the one that we already knew, simply called the distribution of sample proportions. What do we know about that distribution? Well, we know that every time we do a draw out of a population, let's say a population with population proportion 0.5, the population of all possible coin flips. When I draw from that population, i.e. I do 100 coin flips, I know that I'm unlikely to get exactly 50 heads. I'm unlikely to get P as the proportion of successes when I go and dig into that sample. The p-hats that I draw from samples, the sample proportions will vary. They'll form a distribution. But over many, many trials of size n, we see patterns. One, that the center of the distribution of sample proportions, mu sub p hat, will itself be centered on the population proportion itself. We discussed through the binomial theorem that we can calculate the spread as measured by the standard deviation. The standard deviation of p hat is square root of pq over n. And lastly, we had the thing called the rule of thumb that said that the shape of the distribution of sample proportions will be normal as long as NP is greater than or equal to 10. NP is just a fancy way of saying the expected number of successes, and that n times 1 minus p, sometimes pronounced NQ, is greater than or equal to 10, which is just a fancy way of saying the expected number of failures. So about the distribution of sample proportion, we know a great deal. But let's talk about what would happen if I knew the population proportion for a couple of different populations and I did repeated draws. So let's pretend there's a school, call it School 1, in which the students do their homework 70% of the time. And let's say there's another school, School 2, in which the students do their homework only 50% of the time. What would happen? What would happen if I did repeated draws of size 100 from school number 1? I would get p hat after p hat after p hat. Would they all be the same? No. But what do we think is going to be the center of that distribution? About 70%. Imagine if I did draws of 200 students at a time from school number 2. Draw after draw after draw. I expect that all those p hats that I would get from that set of sampling would also be normally distributed and also have its center not at 70% but 50%. Well, there's a piece of software called Fathom that allows us to actually see what would happen over many, many trials, many, many simulations. Here's school 1, and indeed the center of its p-hat distribution is 70%. Here's school 2, and indeed its center of its distribution is right around the 50% mark, right where we expect. Now the third thing that this Fathom software can allow us to do is say, okay, random p-hat from school number 1. Let's get a p-hat from school number 2. So I have 2 p-hats on my hand right now, p-hat 1 and p-hat 2. What would happen if after I got p-hat 1 and p-hat 2, I subtracted p-hat 2 from p-hat 1? I get that number and I plot it. Boom. And it's one of the numbers in that distribution. And I do another simulation. I grab a p-hat from school number 1, I grab a p-hat from school number 2, I take p-hat 1 minus p-hat 2, get another number, the difference between those two p-hat values, and boom, I plot that. And I do that again and again and again 1,000 times. That's a distribution. What do we call that distribution? Well, this first one was called the distribution of p-hat 1. This one was called the distribution of p-hat 2. This distribution is called the distribution of p-hat 1 minus p-hat 2. We call that the distribution of the difference of sample proportions. Now what I really would like to know about that distribution are the big three. The big three, whenever I want to describe a distribution, I want to know its shape, I want to know its center, and I want to know its spread. So, let's see if we can figure out what it is. Well, on this particular drawing, I'd say the center looks like it's going right through point 2. Let me get this straight. School 1 had a 70% population proportion for homework. School 2 had 50%. And then the center of this distribution, called the distribution of difference of sample proportions, ends up having its center at point 2. Is that a surprising outcome?
No.
Why not? Because it's the difference of those two population proportions. And that's exactly what we're going. We're going to note that there's actually a formula for calculating the middle of the center of the distribution of difference of sample proportions. Okay? Can you read that in the back? Not at all? May I write it bigger? Here, I'll write it bigger. Mu of p-hat 1 minus p-hat 2. That's the name of my distribution, the difference of sample proportions. The center of that distribution is equal to p1 minus p2. And again, there's no hats on those. Those are the true population proportions. And that totally jives with what Jacob just said, right? It's not surprising that the center of that distribution of difference of proportions is 0.2. Item number 1. Important. Let's put stars on it because it's that important. Item number 2. What about the spread? What about the spread of that distribution? Well, let me go back to chapter 7 with you. When I wrote something like x minus y, variance of x minus y is equal to variance of x plus the variance of y. Do you remember that? I hope you do. Okay. Oh, there's a condition that's associated with that formula. X and y independent. That's only true if x and y is independent. Well, let's say I wanted to find out what is the variance of p hat 1 minus p hat 2. Well, wouldn't that be the variance of p hat 1 plus the variance of p hat 2? That would follow from that. As long as the two populations don't affect each other, as long as they're independent. Okay, well, what's our next step? Our next step would be to write down what is the variance of p hat 1. Well, I believe it is p1, 1 minus p1 over n1. Kind of looks like the standard deviation formula without the square root. Well, that would make sense. The square of something square root would take the square root away. Sound good? And then what is going to be the variance of p hat 2? Well, I think it would be p2, 1 minus p2, all over n2. And that would equal to that variance of p hat 1 minus p hat 2. But you know what? How many times have we worked with variance in this class?
Never.
What would we prefer to work in, Jacob?
Standard deviation.
So let's do that.
The square root of
Let's
that,
take the square root.
of that sum.
We'll take the square root of that sum, and we'll declare that to be the standard deviation of the difference of sample proportions. Now, that is a nasty formula. It's got two fractions in it, which you don't like. It's got a square root in it that you don't like. The good news is you don't have to memorize it. If you have your formula sheet out, and if you turn your formula sheet to the page that has the boxes on it, and if you look in the boxes under the heading to sample, you are going to see that it's listed as the standard deviation of the difference of proportions. Hooray! You don't have to memorize it. Last part. We might as well finish off the last of the big three with the remaining 2 minutes. What is the shape? What is the shape of the distribution of difference of sample proportions? And the answer is, as you know, we had hoped for, it's going to be normal. But only if N1 P1 is greater than or equal to 10, and N1 Q1 is greater than or equal to 10, and N2 P2 is greater than or equal to 10, and N2 Q2 is greater than or equal to 10.
Q2 is the one minus 2, right?
Yeah, whenever I use Q, it's the complement probability to the P. So 1 minus P. Oh wait, that looks familiar too, doesn't it? So essentially you're saying, as long as we're coming from normal distributions, the difference of sample proportions should also be normal. And that's where we're going to cut it off for right now. All right?
Did we finish the chapter?
Oh no.
Oh, no.
Oh no.
Okay.